Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the 11th and the 12th lecture of computer programming for civil engineers. And in today's lecture, we are going to talk about some new skills in Python programming, and specifically we'll be learning about loops as a lecture 12 part of it. So mainly today we are just practicing more programming skills, and we are going to do all that with the help of a very interesting example of simply supported beam again, but this time this is very unique. We have a simply supported beam of length L, and we have a concentrated load P with Newton units, and if this load is applied at a distance A from support number 1, and that will be in meters as well. What we need to do is we need to find the reactions at point 1 and 2. But not only that, we then have to find out how the shear force distribution and the bending moment distribution looks like. And with this, what we'll also create will be elastic curve, which is called the deflected shape of the beam. And this all will be the part of lecture number 11. In lecture number 12, we will do something very interesting. We'll start placing this load at support 1, and we'll start moving it towards support number 2. While it moves, the shape of the shear force and bending moment diagram and the deflected shape, which is not shown here, will start changing. So what we are going to do is we'll create a loop of changing position of this load P, and this load is in civil engineering, structural engineering applications, it is commonly known as moving load. And with this moving load, we'll figure out the new shapes of shear force and bending moment that can be, and deflected shape, and these can be very useful in designing bridges and other structures where we have load changing its position or sometimes its magnitude. Several such cases are also provided are also provided in this PDF file, which I quickly show you here. So in this PDF file, you will see by AWCORG, it is beam design formulas with shears and bending moment diagrams, but actually it is more than that. We have simply supported beams with different types of loadings, including uniformly uniform distributed loads, concentrated loads. We are today working on figure number 8, actually, which is a concentrated load at any point, not at the center. So it is it can change its location. There are also cantilever beams in it, beams with fixed one end, beams with overhangs, beams with fixed end both ends, and also continuous beams with multiple spans as well. So this is one of the figure, second, third, fourth, and what we just discussed was figure number 8, this one. So here what we will use this figure for, this will be very handy for us for analysis purpose. So if we need to find out reaction here, we'll directly use the equation PB over L to calculate that. So you don't need to derive them all again. You will study them in other subjects later on, or maybe you're already studying them in mechanics. But today we'll be just directly using these derived formulas to write our software. The reaction number 2 with PA over L, the bending moment maximum value if you are interested in, the value of moment at any point A or at any point X actually, and then the maximum deflection in while this load is applied at this particular location. Also the deflection right below the point where the load is applied, that may not be a point of maximum deflection. And then the equations for deflected shape delta X when we are interested in the deflection at any point X behind P, so where X is less than A. This is X and this is A. And then if X is greater than A, this X is greater than A, which means we are here in this area. So in front of P, if we are interested to find out deflection at any point x, then we can use this part of the equation to find that. So we have all the formulas available to us to do our today's lab. So let's start working on it in Spider. So here, as before, I have a blank sheet open for you to start working on, so we can all write these comments on the top that what's this all about. But for now, let me keep it clean to make it more clearer for future reference. So first of all, we know that we are going to play with numbers, and we are going to create array of different points where we need to find out shear force and bending moment. We're not just finding one shear or one bending moment, we want to find bending moment at every point on this beam. So we need to import numpy for that to work with arrays. So let me write import numpy as np. Let me increase the font size a little bit. So this warning sign is telling us we haven't used np yet. So if it is not being used, we can delete it, but of course we are going to use it in our program today. Next, we need to draw graphs, and for graphs there are several libraries available, but for us, we already have started learning Matplotlib library. So let us import Matplotlib library. Specifically, it's pyplot class. So I'll say import matplotlib, and we are interested in pyplot. So we're getting good help here. As plt, for example, again. So with these two libraries, let's start taking first of all the input of different constants. So we have been provided with constant length of this beam. We know the constant position of A. For first part of the lecture, we will work with constant position of the load at A, but then we'll also start moving load P, so A will start increasing from 0 to L. So but then that is for today's lecture 12 part, but for now let's work with constant distance A. So let's say the load P has a magnitude of 10 newtons. Let me go to the next line and define length with small l equals to, let's say, 20 meters. So its load is very small here, but then this is just for the sake of explanation. Usually 10 Newton is just 1 kilogram, so it is nothing, but let's keep it simple. Small a is a constant location of load P, and let it be at a distance of 4 meters from the support number 1, and this is support number 2. So this a has been defined. Now we can easily calculate other variables we need. I just use this gap of a blank line just for readability purpose. We can provide gaps, several gaps in writing code, but we cannot provide horizontal spaces because they will be considered as indents to group or block different code lines. So let me now calculate B as well. We know B will be equal to L minus A. So now we already have defined B. Nothing else at the moment we need now. So we are ready to write our code for calculation of shear forces or bending moments at different locations. But we need R1 and R2 as well. So let me say R1 is equal to, let's pick it up from this equation, PB over L. So it will be P multiplied by B divided by L, and then I press enter to it. Then R2 is equal to PA over L, so it will be P times A divided by L. So we'll make sure that by mistake, if you write capital L, it will be a mistake because capital L is not defined anywhere. So we know that Python language is case sensitive. Now once we have R1 and R2, let's define several points on this beam so that on every individual point we should be able to calculate what is the value of shear force there, what is the value of bending moment there, and then in the deflected shape of the beam, what is the value of the deflection at that point. So let's define the whole space of X first of all. So I would say X is equal to numpy dot linear space and in parentheses we will write first of all the starting point of the linear space, and we want to start it from 0 with the comma where we want to stop x. The maximum value of x should stop at a distance L, which is 20. So let's write L here. Of course, we make sure it is small l. Then we need to define in how many points uh, do we need to divide this whole length. So let's say comma, and here by default it always divides them in 50 points, but let me divide them in 100 points. So which means that the whole length of 20 meters is now divided into 100 small divisions. So every division will be 1/5 of a meter. Which is around 20 centimeters. So once that is defined, let me check it by just printing it on the screen. So I say print x, and let me run the code first time now. So once we run it, we see that all the way from 0 to 20, this has been divided into 100 parts now, so which is working fine for us. Let me delete it because now we don't need it. So now let's plan to write to store shear force in variable v, and let me remark it for now because I'm not writing at the moment, and we are going to calculate bending moment and store it in m variable, and then I want the deflections to be stored in capital D variable. So let's first of all start working for shear force. Now shear force is actually different in the part which is behind P, you can see that, but constant everywhere, and in front of P it is also constant in this case, but it has a very different value. We know that shear force behind this is equal to, if we consider upward being positive, so it is just equal to R1. So here I'll start writing code for shear force, but then I want the shear force to be calculated for every point that we planned at a distance x like this. So let me first of all define 0 shear force line and store it in v. So I will say now v is equal to numpy np dot lin space, and within the parentheses I want the shear force value to start from 0, and I want the maximum value of shear force to remain 0, but I want 100 points like these with these values. So now once we have defined shear force with zeros, let's start assigning all these v's some values. So let me double check first of all. We just print v to see what actually it results in. So it results in 100 values of shear forces at 100 points actually, but then all of them are 0 at the moment. So currently we are at the baseline of shear, and now we'll start changing the values of shear everywhere. So let me delete that, and now we say v, actually we know it is all the way from 0 to a, it is equal to R1, positive R1. So we can say within the box bracket, whenever we have an array, the array value can be accessed with the box bracket. So for example, if I write print x, but in the box bracket I write the value of x at 100, at one less than at 99, for example. So we already know that once we created the space of x from 0 to 20 at we divide to 100 points. So among these 100 points, the 100th point had the value stored as 20, while 99th point had the value stored as 19.7979. Actually, the arrays starts not from 1 but from 0. So 100 points means the 0th value will be the first one and 100th value will be 99th. So this is actually the 99th value, and this is the one value less than that, so 98th. So let me print both of them in separate lines. So I just say I want to access individual values there. So let's double check. Yes, the last value is 20th and the second last value is 19.7979 in more decimal places. So we know now that box brackets are used to access an individual value within that particular array. So we'll say v, but then we already know that here in this line there are 100 values from 0 to 99 spaces. We have 100 values stored in v. Which one we want to access? We want to access all of them where x is less than a, which means once any value of x within these v, we have the values of x, and if they are less than a, then we are talking about only that part of the array. So whatever we write here, for example, is equal to r1. Now all the values from x is equal to 0 to a, which are all actually less than a, will for that the array of v will store r1 only. So it will be r1, 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 r1 everywhere up till here, but remaining will remain blank. So let's print v now again to see what it stores now. We already know from the past that v had all zeros first of all. So let me play it now and see what happens. So you can see that the up till a, it is storing 8, while after a, the length a, it is storing nothing in it. So if, for example, if we increase a from this from 4 to actually 10, which is halfway of the length, so the point load is moving right in the middle now. So we should now note that half of them should have 8 and other half will be 0. So let me double check here. So of course the value of shear force will change because the load has changed its position. So shear force value has changed from 8 to 5, and now the total load was 10 because it is in the center. So half of it, 5 will go in this side and half of it, 5 will go the other side, but then the shear force in the other, that part is half of the shear force diagram is now clearly shown to be 5. So let me change it back to 4 and let me delete this part at the moment, and let me copy this line, or let me write separately. Now v, when we have x greater than a. Now what we are missing is that if imagine a is equal to 4 here, so if the x value is 1, 2 and 3, this will be assigned to it because it tells that x is smaller than a. But if x value is equal to 4, 4 is not smaller than 4. So this will not work. Also 4 is not greater than 4 here, so this will not work. So we should accommodate 4 somewhere as well. So let me accommodate 4 here. So if now I am saying that if the value of x is greater than or equal to a, so including 4, all the values of x from 4 to 20 will be used for v, and there we know that all that is equal to negative of the reaction number 2. So we can write minus r2 for this. Let's now print it once again and see the results. So now we can say all the way up to a, the value of shear force is positive 8, but after a, the value of shear force is minus 2. So we are working fine. So after this, now we can start working for bending moment. So let me write here as a note shear force, and now bending moment. We know that it will be quite similar to this, so let me copy all that, paste it here, and instead of v will write m. So first of all we'll define the blank space of m, the straight line of bending moment with all zero values, and then we need the bending moment values increasing up like this from 0 to a with some equation. We'll check it now, and then decreasing as well. So here is the equation for the values less than a. So I'll change this as well. So now let's correct the equation for bending moment. The bending moment starts from the first part of this equation is for values of x which are less than a, which means for this section, and the second part of the bending moment diagram or the array should cover the values of x which are greater than a, which are after this here. So let's write the first equation. First equation, at any distance x behind the load p, that will be r1 multiplied by x only. So let's write that here. So for r1 multiplied by x, but then what x? Here this moment has limitedly been stored, the product is stored in this moment which has only x values less than a. So here we should also multiply with the x values where x is less than a. So this is the first part of the equation. The second part is now the position where the load, where the section is in front of load P, somewhere here for example. So this distance here, will become our x, and this distance will be x minus a. So the moment about this point is equal to r1 multiplied by x minus p multiplied by x minus a. So let's feed that here. So that will be r1 multiplied by x. Now what x? This time these x are all x values which are greater than equal to a. So they should be x greater than or equal to a, and then finally minus p load multiplied by, in parenthesis, x. And what x? The values of x where x is greater than or equal to a minus a itself. So this is the equation of bending moment. Let's now quickly print it on the screen and see how it goes. So here we have the bending moment at the end is 0, and at the first end is also 0, and it's varying smoothly as it appears, but we'll draw the plot and we'll see and verify that later. So let us now draw the deflector shape. In order to do so, we know that we again need to write 3 equations, but this time for the values will be stored in D, and at the end we would like to print the value of all D. We should start with storing D with all values 0. So the start value and the end value and all of them will be 0, and within and they all will be, so in D, first of all we store all zeros. So we have the starting 0 and ending 0, and all the values in 100 values in between will also be 0. And then in all D's where x is less than a, we need to store this equation. So we'll use this equation to calculate that value, that particular value of deflection where x is less than a. So let's replace it with this one first of all. So it is P multiplied by B. So I'm actually writing the first equation, this one, multiplied by X, but we know which X, where X is less than A, and then this divided by, within parenthesis, 6 multiplied by length at the end, small l, so small l, and then it's also multiplied with the modulus of Flexure Modulus, which is the product of EI, the Young modulus multiplied by the moment of inertia. So let's define it first of all on top here. So imagine that this is a steel beam, so the product of EI is stored in EI as a variable, and in megapascals the Young modulus of steel is 200,000 megapascals, and we use into 10 to the power 6 to convert it into pascals, to the power 6 to convert it into pascals, and now we multiply it with the moment of inertia. So imagine this is a steel beam with a rectangular cross section. So if the width of this beam is W and height is h, so it's W h cube over 12, but in meters let it be W is 0.1 meters, which is 100 centimeters. It's quite big. Let me make it 0.05 meters times 0. So it's a square beam. The cube of it's the height h and whole divided by 12. So now this is the Flexure Modulus, the product of EI, and let's use that product here as EI. And then after this division, it's multiplied with the difference of L square, B square, and X squared. So let's multiply it with, within parentheses, L squared minus B squared and minus X squared. But again the question is what X? So all the X's which are less than and less than A only. So X which are less than A. Now we can see for the second deflection where X is greater than or equal to A, here we have the case greater than or equal is missing here, but then we are also calculating for equal. We're using the same equation as this. It's quite similar to this. So let me create a copy of this one and then edit it to become that one. So quickly let's copy and paste it here, and then it is PAL minus X. So B is replaced with A and LX is replaced with L minus X. So within parentheses I'll say L minus X, which is this one, but this X is wrong. This X should be the X which is greater than or equal to A. So let me replace this with greater than or equal to A. Then we have divided by 6EIL, which is already the same, but then multiplied with 2 times of LX minus X square minus A square. So 2 times of L, not squared but multiplied with just X. So multiplied with X, but which X? The one which is greater than or equal to A, all of them, and then minus X squared. So here we'll have the X, the one which is greater than or equal to A is squared minus A squared at the end. So this equation with A squared ending is fine. Let's print D and see how it goes. So it's a very small number here, and we see that the deflection at the end 2 is 0, and also deflection at end 1 is 0, and it's gradually increasing and then decreasing back to 0. But once we'll plot it, it will be much clearer. So let's start plotting them. We already have imported the PyPlot sublibrary from Matplotlib Library, and at the end we don't currently want to print displacement, so I'm deleting that. And then first of all I'm going to create a blank figure and storing it in variable fig. So fig equals to plt dot figure and blank set of parentheses. We don't need any default values currently in it, so keep it simple. Now we need to create three subplots, just like this one. We need three graphs together, one above another. So this is a one column of graphs and three rows. In the first row we'll put shear force diagram, in the second row we'll put bending moment diagram, and in the last row we'll put the deflected shape or the elastic curve. So we need three different axes to be defined. So let's define all of them one by one. So the first one, I'll define it as so let's define and store first plot of shear force diagram in variable ax1, which is the first axis we'll say, and then the second will be bending moment, and the third will be the elastic curve or deflected shape. So we'll say is equal to fig within the figure fig dot add underscore subplot, and then within parentheses we'll define the position. So we need three rows and one column set of graphs, and this is the first one of them. So once this is defined, so plt dot title, and let's add a title shear force diagram. Let's define the second axis, which is ax1, and equals to figure dot add underscore subplot. This is again the group of three rows and one column, but we are talking about the second one of them. And this time we need to set the title of this plot to be bending moment diagram. Then let's define the third one. This axis should be ax2. The third one is ax3 equals to figure dot add underscore subplot, and this time it is again the same three rows one column, but this is the third one. And this, let's add to this particular plot, let's add a title of deflected shape or elastic curve. Now once that's done, let's for now plot them. So ax1 dot plot, and within parentheses at x we need x, at y we need the shear force diagram because it is ax1 axis, the first one we are talking about. And then we can now start putting other parameters in it too. For example, we need it to be having a color equal to a string of colors, which is, for example, this one be red. And for example, also we are interested in setting the thickness of this plot line that will be drawn, called line width. Let it be equal to 3, for example, a relatively thicker line. Similarly, we'll make a copy of it and 2 more copies. The first copy will be ax2 and its color be green, for example. Thickness will keep the same, but then this will be with the bending moment m. And the last third one is deflection now, and let it be blue with small letters, of course. And let's keep the line width the same. And finally, we'll say plt dot show. So let's run and see what we get. So here we in plots we have figure being plotted. So we are seeing the shear force diagram, bending moment diagram, and the deflector shape as well. So we can see that it's not they're overlapping each other. It's not these things are not well placed. So let's put them in tight order by mentioning at the before showing. We'll say figure dot tight underscore layout. We can set padding to it, but let's keep it blank for the moment, and let's run it again to see the results. So we can now see that the unlike before where we had these overlapping values, we are not able to see the title as well as the access values, but now they are well placed tightly, and now these diagrams are much clearer. So this was what we needed to do in the first part of this lecture, lecture number 11. Let me now change the position of the load and see how it varies. So instead of 4, I put it at 7 feet, for example, which is a little bit less than halfway towards the support number 2. Let's run and see the results. So we can see that how it has changed. Let's check it for position which is 15 meters. So let's run it again. So we can see that how once the load is moving towards support 2, how it is changing the values as well. This was for lecture number 11, and let's start talking about lecture number 12. So in lecture number 12, we need to create an animation of all these graphs where the load P was moving from one side, support number 1 to support number 2. While it is moving, we'll see the bending moment diagram changing shape and shear force diagram as well as the deflected shape, but we needed to create an animation out of it, which can be in the form of GIF file or MP4 file. So let's see how we can do that. So there are several ways of doing it, but the method we are going to use today is called uses another library which is called Collide, which is called Celluloid. So let's see some more features of it online. So if we go to our browser and search for PyPy, we'll see the website where all the Python packages are listed or indexed. We'll go there and then we can search for anything we like, but for now we need to search for something which is an easy animation of Matplotlib, and if I search for it, I'll see that one of the second one is Celluloid. So in order to install that in Anaconda based Spider, we'll go and in the search we'll type Anaconda, and we'll go to Anaconda prompt, and then in the prompt we will write this library name, but before that we'll say pip, which is the Python installer for PyPy libraries. So space install, and then with space celluloid, CELLULOID, and then you press enter. It will take some time, and it will say that some of the requirements required for the library are already met, and then finally it is installed. Once it is installed, it is ready to be used in Spider. So let me close the Anaconda now and just see what Cycloid is to do. So what we can do with Cycloid is, on this website we can create beautiful moving graphs like this. There is a method of how to install it. We just used it a while ago, and then there is an example. So in this example what we do, we create a camera with this library Celluloid, and once that camera is created, then we have our Matplotlib figure, and then we also create a camera on that figure. So whenever we create a plot and arrange something on it, we just say snap, take a photograph of that graph. Then what we do, we keep changing the graph and we keep snapping, snapping and snapping. And once all the photographs of different shapes in the graphs have been snapped, we'll call the camera again and we'll say animate it and store it in an animation or a movie. And then once it is stored there, we'll say save it to either an MP4 file or maybe to a GIF file for a specific format or so. So let's let's apply this knowledge that we got from PyPy into our program. So first of all, what we need to do after installing, let's import camera from celluloid. So here in the start, I'll write import. Either we can write import, or we can also start by writing the same way as from celluloid import camera. So once that is done, and we have already started a figure, let's start a camera as well. So with a camera with a small c is equal to, we can write any name for it, of course, equal to camera. And we created a camera, but this camera should be focusing on something to take photographs, and let's focus it on the figure. So whatever we create in this figure, we can now take a snap of it anytime by just saying camera.snap. Now what we need here is we need to create a graph by changing the values of a. Notice we were changing value of a here, and by every change we saw a different variation of the shape of this graph, and we need to snap this and snap this and join them together as a movie and play them frame after frame, so it will look like an animation or a movie for that we can use or display it in our PowerPoint presentations perhaps, or on our website or so. So in order to create that, we need to recalculate shear, bending moment and D every time we change A. So this means that we need a subsystem here that changes A from 0 to 20, so that once the value of A is 0, the load is at first support, and let me run it for now. So we have 0 bending moment diagram, and then as we start increasing it from to 1, then 2, 3, and we keep going on, as for example 17, and then 18 and 19 and finally 20, we get no bending moment. So the it's all 0, and then the maximum shear is at the support because load is at support at the moment. So but we need to do it automatically. So what we can do here is we can keep it default A, but before drawing this diagram, after defining X here from 0 to L, we make shear force diagram 0. After creating X, all this need to be repeated for all values of A from 0 to 20, and we keep drawing their frames and we keep creating their snaps. So in order to create this frame and snap them, we need to define the figure already. So here after this, for example, we need to use this camera dot snap. Now before this taking snap, the camera should be defined earlier. So this means this statement should be earlier before that. So but then this needs fig, and fig should also be defined earlier. So let me move this code from here. I cut it and I paste it right here at the end where we defined these values. So here, so in this code, first of all we imported our required libraries, then we set our default constant values, and then we defined our figure and our camera that is looking at that figure. Then we calculated some constants, and then we defined the all x from 0 to L, and now we need to start a loop that will change value of a here, wherever in all this group a is used. We need it to be first of all 0, then 1, then 2, and so on. So here what I'll start is called a loop, and the loop is for there are several types of loops in Python. The loop we are talking about now is a for loop. So I'll say for, and then I'll define a loop for I in x, for example. And as you know, whenever we create a block, we have to close it with a colon, and like once we define a function, we use colon for that purpose. And now we need to press give some space here as an indentation to define that all this is repeated whenever the value of x will change. So what it will do is, for every value of I in x, so x, we already know x, once we defined it here, it has 100 values. So for every individual value of x, by calling it currently I, let's do all this. So first of all, I will be the first value of x, then I will be second value of x, then all this will run, then I will become the third value of x, so then again this will run, then I will be the fourth value of x, and we know what are all these values. So because the length is 220 meters, and we already have divided it into 100 equal parts, so that will be 0.2 meters each. So I will be first of all 0.2, and then 0.4, and then it's 0.6, and that is the I that we need to be replacing a everywhere. So instead of replacing a everywhere, let me mention here that a, small a, is equal to I. So once the value of I will be 0.2, it will be stored in a, and wherever a is used throughout this area within this block that we have defined, the value of a will be replaced by I already, and then in the next loop it will take the next value of I, and whenever it will be running all this, at the end it will take a small photograph of it, and that photograph will be of what we already have said, that photograph the figure. And where is the figure? Figure has been used here actually, so this is a wrong place to take a photograph. So let me cut it from here and paste it right at the end before showing the plot. So now I need to indent all of them again. So now once the value of I will be the first value, which is 0, and the second value is 0.2. So once I will be equal to the first value 0, a will become 0, and throughout this code wherever we have a, it will be replaced by 0 and calculated. A complete bending moment diagram will be drawn, complete deflected curve, complete deflection curve, and complete shear force data will be recorded. And then along these three axes, the value, with these titles, the value of shear, bending moment, and deflection will be plotted. Once they are plotted, it will be arranged tightly, properly, beautifully, and once that arrangement is okay, a camera will take a snapshot. Now notice the last line is not indented, so this means this whole block is complete. So it will go back here, and then start with the next value of I, which is 0.2. So a is equal to 0.2. Everywhere a is replaced by 0.2. New values of m, d, and v are calculated. Then new graphs titles defined again, and the new graphs are plotted with the same color, and then arranged beautifully, and then another photograph has been taken and stored. and then the next value until all values of x are used for position of the load, and we have all the photographs taken from 0 to 100 frames for the length change of 0 to 20 meters of motion of the moving load. Now after that we need to save it in MP4 file. So first of all, after all these photographs been taken, we need to go and remove the indent, because we need all of this to repeat 100 times, but we don't want this statement to repeat 100 times. So here I'm saying writing a variable name, for example animation. I'm taking the idea from this help file here. So animation equals to camera dot animate. So what this will do is, camera has taken 100 snaps. Now it will connect them together in the form of a set of frames in a movie. So first frame, and then second frame, third frame, fourth frame, and about 100 frames. So once it will show these frames one over another, it will look like a movie to us. And after that, once it is done, let us save it in a file by the name of Shear Force, or let's say beam analysis MP4 file. So I will say animation dot save, and within parentheses I'll write the name of the file I need. So let it be at the moment beam analysis dot mp4. Now notice I have saved this file lecture 11-12 in a folder. Let me save it again and show you the folder. Save as. It is in my lecture pi files folder, and it is by this name. Now once I will run it, and I'm replacing it now, once I'll run it on this in the same folder, an mp4 file will be created. So let me open the folder for you here. So here you will see there's no mp4 file. So I will go back to the code and run it. It is taking some time. It is giving some warning that in the future version of Python, some of the code will technique will change. It will become much better. But for now, this is what it is. It is taking some time in creating all these frames. We are waiting for the message to appear. So here it is. The message has appeared, and it is showing some error to us, saying there is an unknown file extension of mp4. So let us save it to a GIF format, for example, which is no audio format for an animation. So let's try it again. So notice it is still working. I'm waiting for the last message to appear. Okay, it's done, and the GIF file, here it is, beam analysis GIF file is made. Let me double click to see the results. Beautiful. So now once the load is moving, we can see that the shear force and bending moment diagram is changing its shape. Deflected shape is also changing, but there is something wrong in the shape. I'm not happy with that. There is something wrong in the calculation of bending moment and the deflected shape. So let's find the error and correct it. So shear force, we found it to be working fine. Let me draw. The deflected shape should have negative values, so let me change that to negative. So I'll write -d here. Now the other mistake is that once we are calculating the shear force, for example, the value of R also depends upon A, and also the other R also depends upon B, while we are changing the the position of the load. As with changing with I, A is changing, the calculation of B as well as R and R1 should also change. So I'm cutting this from here and also pasting it right below it. So let me put a tab here and a tab here as well. So now once the value of A will change to, for example, 0.6, now new B will be calculated, new reactions will be calculated, and these reactions here and here and other values will of B that are used here will be recalculated for the new position of load, and then it will be animated as before. So let me run it once again and see the results. So once I'm running it, it is going to overwrite that GIF file for us. Let's wait for the last result here. We'll see the last figure here as well. Let me clear all from here to see. Once it will draw this PLT show, it will show the final plot to us at the end once it has been drawn. So it is the final plot because there is load right at the end. There's nothing to show. So this is the last figure it is showing. Let's see the animation, how it went this time. Now it is deflecting as the load is moving, and the bending moment diagram is showing that the bending moment is increasing all the way to 50, and then the maximum bending moment is 50, and then also we see that the maximum shear remains to be 10, while the deflection went all the way up to 0.02 as well. So starting again, the deflection is increasing and increasing and increasing. We are having almost a maximum deflection of 0.01 when the load is in the middle, and then as it moves away from the middle, the deflection reduces, and once the load reaches to the support, there is no deflection in the beam. Excellent. Our software is working perfectly fine. We can have this animation as GIF. We can paste it to our friends on WhatsApp if you like, or you can paste it on your PowerPoint slides for presentation. It will be beautiful animation on it. This concludes today's lecture. So the new things that we have learned today mainly involve the for loop, which can take values from an array one by one and apply to an indented set of code until all the values of the array are consumed. We'll look into loops more in coming lectures as well. The second thing we learned that we can actually use the celluloid library and its camera to take snaps of our photographs or anything that we have created, or graphs we have created in our code, and then we can actually compile a GIF or maybe MP4 video if you want to add audio in it too. In today's lab, what you need to do is I've given you the link of the PDF file which has all types of beam design formulas with shear and bending moment diagrams. You can choose any of these diagrams except figure 8, because figure 8 is the one that I used in my lab today, but you'll choose any other figure, for example maybe figure 10, and then you have to implement that in the same way as we did in today's lab. So the only difference will be you are going to repeat everything what we did today, except the formulas that you will implement should be from any other figure beside figure 8. Notice that in figure 10 there is no deflection, so you may avoid using this, but perhaps figure 9 has equations for deflection, and other figures do also have, like this for cantilever beam, it also has deflection equation. So whenever you see deflection, bending moment and shear force equation, just use that figure and submit your lab for today. Thank you very much and best of luck. Assalamu alaikum.